Here's a real quick video introducing the concept of a derivative, which we will start with on Tuesday in class. So you're familiar with being able to find the slope of a line if you have a straight line. What we're going to deal with a lot in calculus is finding the slope of a curve. And when you find the slope of a curve, it becomes a little bit different because the curve has different slopes. If you're at this point, the slope is some positive number. If you're at this point, the slope is about 0. If you're at this point, the slope is some negative number. At this point, the slope is 0. So if you picture yourself walking along this curve, you're walking uphill. You're at the top, it's somewhat flat. You're walking downhill, you're walking uphill. So you can see the slopes changing. The way we define a slope of a curve is the slope of a curve at a particular point is going to be equal to the slope of the tangent line at that point. So at this point, the slope of this curve is 0.45, which is different than if we go to a different point. Let's change it to, let's go 1. So you can see here the slope is a negative number. So the slope of a curve is defined to be the slope at one particular point. And the idea then, if we want to find the slope of a curve, is to find the slope of that particular tangent line. Okay. The problem with finding the slope of a tangent line is we only have one ordered pair. And if we want to find the slope of a line, we need two different ordered pairs. You have to do y2 minus y1 over x2 minus x1. And therein lies the problem of finding the slope of a tangent line when you only have 1 point. So to get around that, what we do is we create a second point. And the second point is going to be h units away from our given x value. So whatever h is, we're going to go that many units away from our x value. That creates a second point. And now we have a secant line, a line that goes through 2 points. And the secant line then is going to be somewhat close to the tangent line, but not exactly. But the idea is if we can get this point Q closer and closer and closer to point P, then that secant line is going to get even closer to the tangent line. So in black here you have the slope of the tangent line, the 0.59. The slope of our secant line is 1.56. Again, not very close. But let's see what happens as h gets smaller and smaller. You can see the slope of the secant line, the green line, is getting closer and closer to the slope of the tangent line. And the closer h gets to 0, the closer q gets to p, and the closer our slopes become. So let it run. You can see that the secant line slope in green is getting closer and closer to the tangent line slope in black. And that, in essence, is the idea behind a derivative. A derivative is nothing more than the slope of a tangent line. A derivative is a slope of a curve at a particular point. So the definition of a derivative, here in red, is going to be, it's nothing more than a tangent line slope. And it's going to be the limit as h approaches 0 of f of x plus h, that's your y value for q, minus f of x, your y value for point P, over, this is going to be x plus h, your x value for Q, minus x, the x value for P. So this is nothing more than y2 minus y1 over x2 minus x1. If you do your x plus h minus x, that gives you just h. And this is why we've been looking at limits. Notice here, if you do direct substitution, and let h be 0, you get f of x minus f of x is 0 divided by 0, which means try something else. So just a real quick introduction to limits, or to derivatives using limits. We'll look at this more on Tuesday.